Hey, welcome to The Explainer. Today, we're going to talk about a really common part called the potential relay. It's designed to protect motors, but the way it works is just fascinating. We're going to uncover how a motor's own wiring can act like a secret power transformer, creating the exact signal this little device needs to do its job.
Okay, let's just jump right in with a question that honestly seems like it breaks the laws of physics, right? If you're feeding a motor, let's say 240 volts, how on earth can one of its internal parts suddenly see a voltage over 300? It's not magic, I promise, it's physics, and it's the absolute key to understanding how this relay works.
So, to really get a handle on the relay itself, we first need to back up and understand the problem it was built to solve. Think about it. Getting a heavy motor spinning from a dead stop takes a huge initial burst of power.
Now, inside the motor, you've got two different sets of wires, or windings, and they have totally different jobs. The start winding is like a sprinter. It's made of long, thin wire, which gives it high resistance and a ton of explosive torque to get things moving. But the run winding? That's your marathon runner. It's got thicker wire, lower resistance, and it's built to run efficiently all day long. And that sprinter? Well, he can't run a marathon.
And this is the really critical part. That powerful start winding is absolutely not designed to stay on. If it's still getting power more than a second or two after the motor starts up, it just draws way too much current, it'll overheat like crazy and burn out, and it'll probably take the whole motor with it. So we need some kind of super fast, super precise automatic switch.
So, how does the motor know when to flip this automatic switch? Well, this is where we get the answer to our voltage mystery. The real magic isn't actually in the relay, it's happening right inside the motor's own spinning core.
You see, as that motor gets spinning faster and faster, it's not just a motor anymore. It also kind of becomes a generator. The spinning rotor creates its very own voltage, an opposing force they call back electromotive force, or just back EMF, and it pushes that voltage right back onto the windings that are powering it.
Now, this back EMF is where it all comes together. Because of it, the two windings start to interact with each other, and they start behaving exactly like a transformer. The run winding, which is always on, acts like the primary coil. And the start winding, sitting right next to it, acts like the secondary coil, picking up energy through induction.
And boom, there it is. That's the answer to our puzzle. Remember how the start winding is made of really long, thin wire? That means it has way more turns, or loops, than the run winding. So when that back EMF from the run winding gets induced onto the start winding, the voltage gets amplified. It gets stepped up. The motor's own design creates a hidden, built-in, step-up transformer. There's a great saying that just sums this all up perfectly. It's the exact same physical principle that makes that big transformer on a utility pole work. The only difference here is that it's all happening between two coils packed tightly inside a motor. Okay, so now that we know where this crazy high voltage is coming from, let's take a look at how the potential relay cleverly uses it as the trigger for that all-important switch. Pickup voltage. This is the term you gotta know. See, the potential relay isn't paying any attention to the regular voltage coming into the motor. It's designed to completely ignore that. It is waiting for one very specific thing, that high induced voltage to build up on the start winding. That target voltage is called the pickup voltage. So, to put some real numbers on this, for a standard 240-volt motor, once it gets up to about, say, 75% of its full speed, that back EMF will induce a voltage on the start winding that climbs way past 240, all the way up to around 330 volts. That is the signal the relay has been waiting for. So you can think of the relay as just a tiny voltmeter that's attached to a switch. Its little coil is wired right across the start winding, and it's constantly measuring the voltage potential. As soon as that voltage hits the pickup rating, the coil becomes an electromagnet that's strong enough to physically pull in a plunger. That opens the switch contacts, and just like that, cuts the power to the start circuit. So look, this is some seriously cool physics, right? But why does a technician out in the field actually need to know about this internal transformer stuff? Why does it matter?
It matters because if this goes wrong, it's a domino effect of disaster. If that relay fails to open, either because it's broken or, more importantly, because it's the wrong part, that start winding never shuts off. It just keeps drawing way too much power, it overheats, melts its insulation, and completely destroys the motor. A tiny, inexpensive part failure leads to a catastrophic, very expensive one.
And this right here is probably the most important thing to take away from all this. You cannot, I repeat, cannot just swap in any old potential relay that looks like it fits. If a motor is designed to only generate 270 volts of back EMF, but you install a relay that needs 330 volts to pick up, That relay will never, ever open. You have to use the exact relay specified by the manufacturer for that exact compressor. The ratings have to match. You know, once you understand this mechanism, it really changes how you look at the whole system. It's not just a box of random parts anymore. It's this interconnected system where one component's normal operation actually creates the trigger another one needs to function. It makes you wonder, what other simple-looking parts are out there, just hiding these elegant physical principles in plain sight?